Diane and Alyssa, good morning.
Good morning.
You guys stoked? Final chapter? Chapter 14. Last one, then it's a break.
I was looking through the homework and I actually just had a clarification question about number 2 on the first assignment.
You are referring to, what do you mean, 13.5? What do you mean first assignment?
Yeah.
Awesome, go for it.
So when they say the XZ plane, is that just a plane that's parallel to the y-axis? Or did they forget XYZ? Is that a typo?
No, like the XY plane would be the plane that has a Z value of 0. So in other words, it's the plane you're used to working in. So if they say XZ plane, that means the Y is 0. So
Okay.
it's literally going through the Z axis and the X axis.
Okay, yeah, I wasn't sure if that was intentional or.
No, that was intentional, and that's a really good question. As well. All right, let's see if the technology is working today. So we are starting chapter 14.1, which has the ominous title, Vector Valued Functions. But the extremely good news about this is that this is just another name for something that you already know. And so that is what I wish to make sense of today for you. Let's see. How come there's only 4 people in here? We're not that early, are we?
I usually show up 5 minutes late, so I wasn't sure if this was the norm.
Caesar, how you doing? I haven't talked to you for a long time.
Tired. Trying to keep up with all the homework and the projects and the essays. Yeah.
Are you laying sideways in your bed right now?
No, I'm actually in front of my computer looking at my 3D printer.
Awesome. Well, vector valued functions. Let's kind of just get right into this. But the good news is everybody knows what AKA stands for. Also known as just a parametric equation. Which is actually what we've been working with. All those T's, like we have a line and it's made of T's. That's a parametric equation. So you actually kind of already know this. But today you'll get to see a little bit of kind of what the power is of this. So 14.1, we're really just kind of trying to introduce the idea a little bit, and then we'll go on and do some calculus with it. But fortunately, the math of this is really easy. I mean, you already know it all. Like we're going to take derivatives and integrals, but we're going to do it in this world. And that just turns out to be really a powerful application. So I think I can make you appreciate that based on based on what you see in GeoGebra. So let's do that. Let's see, what do we want to do to introduce this? Let's get rid of that. All right, I'm going to share a different screen. It's a trip. There's like 3 of you here today. I still don't get it. Let's see. So you guys are you seeing a black screen now, or are you seeing GeoGebra?
I'm seeing your desktop with the RCC
Yeah.
wallpaper.
Same here.
That's just weird. I don't get why I can't get you guys to see the other screen. I don't like that. Because this is too small.
Now I see GeoGebra.
Yeah, so I drag GeoGebra over here. Okay, so I want you to think about this for a second. Notice the parametric equation that I gave you, and we're going in this direction now. But notice the equation, it's just 2-dimensional. Notice I didn't give a z component to it. I just said cosine of t for x and sine of t for y. You shouldn't actually be super surprised that that's just a circle. And notice, again, the thing you got to get good at visualizing now is the ground is sort of the old XY plane. And remember, we memorized, I guess, that the red was X and the green was Y. And so this is just a circle. And we studied that in this class. This is a polar equation. This is the polar version of a circle. T is, we think of T as maybe time, but in this case, it's really an angle. That's the parameter. And let's see, do I want to say something about that now? I'll say something about it later. So that's really cool, that's a circle, and that's awesome. But I want you to watch what happens to this. I don't know if I can add to this. Let me see if I add to this. But I want you to think about, what if I added a z coordinate to this? And let's say that z coordinate was, well, again, hopefully this will work. Sometimes it doesn't like me to edit, but what if I put a 2 there? What's that going to do if I put a 2 there in the z?
It's going to move it 2 in the z direction, right?
Yeah, because notice every single point is the same circle as before, but now the z coordinate is 2, right? So you'd think, unless something's going wrong here, yeah, that just moved it up. So that's kind of cool, because now it's 3D ultimately. And so, of course, if I change that to a 1, you think, I know what's going to happen now. So if I look at it sideways, yeah, look, every single point has a z coordinate of 1. And so this thing is kind of well, I guess you could say it's a 3D graph now, maybe for the first time. But now I want to ask you a really surprising question, which is, what happens if I change that 1 to a t? Now, what you have to think of is, and let me, actually, I'm going to go down here and do something else first. Let's say,
is it going to make a sphere?
Yeah, is it going to make a sphere? That's exactly what I want you to be thinking. Like, what's that going to make?
Maybe a hollow cylinder.
Yeah, maybe a hollow cylinder. Notice it's really hard to visualize. I love what you guys are thinking here. Let me show you something just for a second here. So notice I just graphed a point. In other words, what it takes to graph that circle would be, well, you're letting t be everything, right? So you're letting t be, and let's modify that a little bit by saying we're just going to work our way from 0. Let's see, don't I have control over that somewhere?
They could be in slider at the top.
Slider, duh, thank you. I think that'd be obvious to me, but it wasn't. And so you know that a full lap around a circle is 2 pi, which is about 6.28. So are you surprised the point is right there if I'm at 0? Again, I just want to grow your intuition here a little bit. Are you surprised that the point is right there? Well, you shouldn't be. Maybe now you're not surprised. Because isn't that the point where the angle is 0? So if I'm at the angle is 0, cosine of 0 is 1, sine of 0 is 0. And so we're looking at the unit circle right here, right? So the angle, in this case, t is really kind of like theta, not time. So as soon as I let the angle get bigger and bigger and bigger, then I cruise all the way around this circle. And so there I am. But notice the entire time, what is z? It's 1 the entire time. But if I come back here and I put a t in there, then if I put t in there, then that means this point right here, the y coordinate will be 0. You agree with that? I'm sorry, the z coordinate. The z coordinate will be 0. So it'll be that same point right there, but then the z coordinate will be 0. Well, when I move to right here, that point's still right there, except for the z coordinate is now 0.5. And then the z coordinate is 1. And then the z coordinate is 2. In other words, that point is still on the circle, but do you see how its z coordinate is actually growing, growing, growing? Any more thoughts about what you think you might see?
Like a big opening funnel, maybe on both sides.
I
Or
love it.
spiral.
A funnel, a spiral, a cylinder. It's like really, it's cool. I mean, I love what you guys are doing. You're just like conjecturing and reasoning and thinking. And so now I think I've aroused your anticipation enough. Let's go see what it actually does. Boom. And I'm going to go down here on this here and do the same thing. So now my point will actually stay on the graph as well. Let's see, and let's set this back to 0. So from the air, this thing still looks like a circle. Now, how come we don't see the entire circle? Well, it's just because I haven't zoomed out far enough. So do you agree? It's like it hasn't changed at all. It's still a circle. Well, of course it is, because look at its x and y component. Cosine of t, sine of t. Its x and y coordinate have not changed. It's still a circle. But the whole time we did this, t was actually getting larger and larger and larger. So notice as I slide along this is my a value, which is t, right? The only difference with a and t is a is just a constant. So I'm actually, treating it like a number. A is now 0.4. Remember, t means it's going to take every value from 0 to 2 pi. That's why we have a million ordered pairs. That's not a curve. It's a million ordered pairs that are touching. But now you can see them one at a time. And so does it make sense from the side? This thing's going to just get taller and taller. Notice that's a little weird. Do you see how it doesn't look like it's on the graph? Is that true? Is it not on the graph? Is something wrong with this?
If you look top down, I think it'll act as if it is. So the circle's still going. It's still going in a circle, but I don't think it's going to move up along the Z.
Well, it should. Oh, I know what's wrong. What's wrong with what I typed over here?
It needs T's instead of A's.
The other way around. Like I chose A. A is my T value. And so T should be A. There we go. So this looks like nothing has changed, right? It just, that value, that point cruises around the curve. But again, notice A is 4 right now, right? In other words, the Z coordinate of this point is actually 4. So it still looks like a circle, but that point is actually, all the points are basically climbing up in the air, because basically the Z value, every time you jump to a larger T, then you're actually getting a larger Z. And so, if you will, our circle now just kind of lifted up in the air. Well, this is a vector valued function. Now, what does it mean that it's a vector valued function? Well, it really means this. Good thing you guys are here. This is a really bad day to miss.
Yeah, sorry, I was a little bit late.
Oh, cool. Who else is here? Raymond's here. Awesome. I can't see everybody's picture. Yeah, glad you're here, Raymond. So really what this section is talking about is this. We're actually talking about a vector. And so that A point right there is not just kind of the coordinate of a point, which it absolutely is. In other words, it's just an equation, except it's defined according to the parameter t. But the reason it's called vector valued is it's basically like all of your equations now are going to be kind of emanating from 0, 0, which I just labeled as B, and then they're going to aim toward whatever that point is that you're at. Now, of course, it doesn't like it. One thing about this program, it seems really picky. So vector from B to A, there we go. My period of failure has ended. Let's get this spun in an interesting location so you can kind of see it working. Well, if I go back to here, really the way this function is defined is it's entirely defined by a vector. In other words, this vector that I just drew from B to A is basically just pointing into space. So it's pointing, the vector just points at the point that you happen to be at. So that's why they're called vector valued functions, because they're functions now in 3D that are really just defined by the vector. And really this equation right here, kind of the A equation, that is the vector. I mean, that's the parametrically defined equation. So our equation 1 up here, if I turn everything else off, that equation right there that's turned on is a vector valued function. But do you see that it's just parametric? Like we've already been doing this. This isn't any different than it was before. But that vector right there, because that's kind of how we drew it, isn't it? I mean, didn't I draw? The only difference is with the actual black equation, all the vectors are there simultaneously, whereas I've set it up so that you could just see them show up kind of one at a time. In other words, the vector is just pointing at, you know, one particular point that I happen to have graphed. And so there it is. But that's kind of how these are defined. I mean, isn't that kind of cool? I mean, it also creates really kind of interesting shapes. So what I want to do today a little bit is kind of grow your intuition about why these look the way that they look. And that's kind of what it comes down to. So let's just stare at a couple practical things, because there's some of this comes up in your assignment. So things that I'd want you to be able to do for your assignment tonight. So in a sense, we started with kind of our warm-up example. We started with the circle that you used to just call x squared plus y squared equals 1. You agree with that? But then I gave it this weird name. Well, where did I get that? In other words, if you have this, well, rectangular version of the circle in 2 dimensions, so rectangular in 2 dimensions, because we just have an x and a y, then if a person wanted to write that as a parametric equation or according to a parameter or rewrite it as a vector valued function, how do you do that? In other words, how do you get t's involved to this with this? Well, one option is just to say, I'm going to let x be equal to t. Like that's how I'm going to get a t involved. And this turns out to be not the best choice when there's some squareds involved, and I'll show you that in a second, but that's one option. Okay, well, if that's true, then you would say, all right, t, if I put t in for x, then that'd be t squared equals, or t squared plus 1. And then you could also say, all right, well, then if I solve for y, then your y value would be the square root of 1 minus t squared. And you may remember that's only the top half of the graph, so that's not that great of way of doing it. So if you will, it's vector valued function would look like that. So and by the way, these vector valued functions are oftentimes kind of abbreviated with an R, and the R is for radius. Did you see that vector cruising around? It was like a radius the whole time. It was like the distance pointing straight to the point. So then you would say, okay, great. Well, what's your x coordinate? It's t. What's your y coordinate? The square root of 1 minus t squared. That's a vector valued form, or as I said, just parametric. It's not, there's nothing new. Vector valued form of the circle. Now, you happen to know that there's kind of a better way to do this. This is not so good, you might say, to kind of let that be your intro. But what is really good is if you let x be equal to, well, I think I'll go ahead and stick with the usual. If you let x be equal to the cosine of t, not just x equals t, but x is equal to the cosine of t. That's a very creative choice. Like, how would you think to do that? That's not something you would naturally think. But remember, here, you're only getting the top half, so to speak, because remember, that's actually plus or minus. So if you let x be the cosine of t, then just like above, you'd say, okay, well, if I let x be the cosine of t, and I'm just replacing it with this, then I'd say, okay, well, then that's the cosine of t squared plus y squared equals 1. Great. What does that mean y is? Well, y is equal to the square root of 1 minus cosine squared t. But why is that particularly wonderful? Does this jump out to you as the fact that we're not done yet?
That turns into sine.
Exactly. 1 minus cosine squared, according to one of your identities, is actually sine squared, right? And so this is actually equal to the square root of sine squared, which is actually just the sine. And so now a better parametric representation for this thing would just be x is the cosine of t, and we just discovered that y was just the sine of t, which is a much nicer answer. It doesn't have that limitation of only being the top half. And it's cleaner, like it's just kind of a nicer answer. So that's actually better. And so that's what I just did, in a sense. That's what I just gave you from the start, was a more creative substitution as to how to kind of make that happen. And I want to spend a little more time talking about that today. And of course, we're really talking about those 3D equations, not just 2D equations. But that gives you a little bit of insight. And maybe I'll just add the quick note here that I said out loud, which is this is often used because it kind of that stands for radius, since these are vector valued functions. Well, let's go play. Let's go play around with something else here, kind of a second example. What do you think this might look like? So this time we're going to go 3D. I'm going to give you an X. This is really an interesting graph. I think I just discovered this on my own, but I can't remember for sure. One of the things that's kind of fun about this is just to kind of play around. What do you think that might look like? Now notice it has the T that it had before. So if you wanted to kind of analyze, like predict what this would look like have a little intuition rather than just kind of immediately go over, just like you did before. In other words, if I say the equation is y equals 3x plus 2, you have the intuition. It's like, hey, I know what those look like because there's just an x and a y. That's a line. I already know. And so you go graph it and you're sort of set. But whereas the person that doesn't know anything says, I don't know, I'll just graph it and anything could appear. And so, what might this look like? Well, does what we just did a second ago help you with this? In other words, what I find myself thinking is, what does this thing look like? What would I see in kind of the XY plane? In other words, if I just kind of ignored the T for a minute, does it make sense that's going to define what this thing looks like from the air? If I look straight down in it, like last time it looked like a circle, well, this time, and you should not know this time, like you should stare at that and think, well, it's still got a cosine and a sine. And so maybe it's going to have kind of a circular look to it, but it's not going to be a circle. Maybe it's an ellipse or, one of the other conics that we studied recently, a parabola or an ellipse or a hyperbola. Maybe it'll look something like that. I don't really know. But then because of that T, what's it going to do at the end? If it looked like, let's say it looked like an ellipse from the air, what's it actually going to do because of that T?
Is it going to spiral up to it again?
Exactly. It's going to kind of spiral up along the path of the ellipse and kind of make it 3D. And so it's kind of neat when there's just a T added to the end. Now I can add weird stuff at the end, like I could add log of T, I could add T squared, I could say the sine of T, all kinds of crazy stuff. But just to start with, let's play with that. So I'm going to go over this time to Desmos, and I'm just going to graph. Actually, can I do this in, let's try it in GeoGebra. I'm not sure if I can do this in GeoGebra or not. Actually, there's something telling me I can't. Let's just go to Desmos first. It's nicer anyway. So you saw before when we did parametric equations that you can type parametric equations in here. So all I'm going to do is type the X and Y coordinates we just had. So 4 cosine of 2t and then 2 sine of t. Notice I didn't control this, but it says t is going from 0 to 1. And you might understand that in this case, because we're talking about trig, we'd at least need to see 360 degrees or 2 pi, right? So what it put there is really not all that great. I'd kind of like to at least go to 2 pi. And so that probably surprises you a little bit. Like, it's a parabola. That's kind of weird. So notice it's not 3D, and I'm just looking, again, you're hopefully you're growing in your 3D intuition in the sense that you're looking down now on a flat plane, and this thing is going to come toward us as soon as I add a T to it. And I can't do that in Desmos, by the way. It's going to say error. It's not designed to graph something in 3D. But could you picture how this gets traced out? Again, I want to do what I just did a second ago, which I think is kind of helpful. If I go back in here and I say, let's graph the point. So I go in here and say, let's start out at A as 0. And I want you to think for a second, what is, if T is 0, which point am I at? Like, can you plug T as 0 into this and like reason out, or maybe even use your calculator if you have to sort of figure out what point am I at? I want you to think about that.
Well, cosine of 0 is 0, so it'd be on the x-axis.
Cosine of 0. Cosine of 0 is not 0. What's cosine of 0?
Oh, I mean 1. 1. That's
1. Exactly right. 1. What's the sign of 0?
That's the 0.
That's the 0. And so you're at the point, well, you would be at the point 1, 0, except for notice we're multiplying by 4. So you're at the point 4, 0. So does that make sense? That's not surprising. That's where you are. Now, what's going to happen is I start to let A grow from 0. Well, remember in this case, A actually is kind of behaving like an angle. In other words, it's going to work its way from 0 to pi. Maybe I should go in here and set this thing to kind of work its way from 0 to 2 pi. So, okay, there, let's get to pi. So where's pi? Well, pi over 2 is 1.57. So notice it actually looks like it reaches the end over there right at pi. That's kind of interesting, right? Pi over 2. But then what does it do? Oh, that's weird. It actually retraces its steps. So it retraces its steps, and then it gets right back to where it started at pi, which makes sense, right? Because isn't the cosine of pi also, wait, cosine of pi, oh, but it's 2, right? I'm multiplying by 2.
Cosine of pi, that's -1.
Yeah, let's see, the sine of pi, sine is a y coordinate, so the sine of pi is 0. But the cosine of pi, well, notice it's being multiplied by 2. So the cosine of 2 pi, oh, that's 1. Yeah, the cosine of 2 pi is 1, and 4 times 1 is 4. So yeah, that makes sense. I'd be back at the point 4, 0. And then when I keep going, notice it goes all the way out to this end. And you may have this memorized, but was it 4 points? All of a sudden I'm thinking, I don't have it memorized. So 4.71, that's 3 pi over 2, I forgot. So notice it hits 3 pi over 2 over there, and then it works its way back to, well, 0 again. 6.28 and 0 are the same number. So did you see how that traced? So I want you to try to visualize when I come back, when I go to GeoGebra and add a t to that, what's going to happen to this? Well, it starts here. Can you picture the z coordinate of that? Can you see it coming towards you? It's coming closer and closer to us. The more I go, it's lifting up off the page. It gets to right here. And it just continues to lift off the page and it's getting closer and closer to us every time I move. Do you see that? Like, notice what now? A is 2.85. Well, the y coordinate, I'm sorry, the z coordinate of that tortoise is going to be 2.85 right there. Can you picture what this looks like?
Yeah.
It's kind of a challenge, isn't it? Well, let's go over here and do it. If I say this land, let's see, I didn't have to say anything, right? I just said, I just started typing, and I think it gave it its own name. So 4 cosine 2t sine 2 sine of t, and then t, boom. So the question is that what you thought you would see? Again, what does it look like from the air? A parabola. We already knew that from 2D, but what is it doing? Is that what you thought it would do?
Yep.
Remember, as it marched along, wasn't it getting higher and higher and higher? It hit right here and just kept getting higher and higher and higher. So it's like climbing a parabola. It's like weaving its way up a parabola up into the air. Isn't that kind of cool? And so that's actually one complete lap. And so what makes this really cool ultimately is you're creating shapes now that kind of live in 3 dimensions. And this is like a path. I like to think of this as like a path. So I can imagine, for instance, a bird taking off of a tree branch and, you know, flying along some crazy path like this, or, you know, a leaf is blowing in the wind, or it falls out of a tree and, you know, the wind blows it around. It's following this kind of crazy path. This isn't any different than what you've done all your life, which is you've just made cool looking graphs. It's just they were stuck in flatland. Does that make sense? They were stuck in flatland, and now they're not stuck in flatland anymore. They can actually live in the real world. I mean, the first time I took this, I thought, wow, I didn't realize, like, all those years I've studied algebra and calculus 1 and calculus 2, I didn't realize that I was living in flatland. Like, this didn't apply to, you know, things that existed kind of in the real world. But can you already see that there's a bunch of calculus questions here? like, you know, what's the rate at which you're climbing here? It's like climbing, right? It's got a slope. If this was a bird kind of flying or an airplane flying along this path, it's got slope to it. It's got length. I wonder how long that line is. That's kind of cool to think about, right? Like those are the calculus questions we'll be tackling here shortly. Today is just, can you get your mind around what these things actually are? Again, just to increase your intuition about this, I want to just quickly do what I did before, which is graph a point so you can watch it happening. Whoa, what in the world is that? There better be an undo button here. Undo. Oh yes, there is an undo button. I'm so happy. Oh, that's because I typed A. It gave it the name A and I tried to use A again. I always find that this just doesn't have the same match. And the other thing I can't really do very easily on this is copy things. So I want to graph a point just like I did before. I'm going to call this point. So I'll graph A again, just like I did before. Say 0, 0, 0. So you can see the vector part of this. And then B will be this point that's actually on the curve, which we found by going 4 times the cosine 2t, except for I'm going to use the constant A, so I don't get all values of t. And then 2 times the sine of t, except for I'll use A, and then A. And so there's my point. Notice it isn't liking it for some reason. What isn't it liking? Maybe
You
it
got to
doesn't
call
like
it a vec. No.
I'm just trying to graph a point right now. Maybe it doesn't like there's parentheses. There's no parentheses around what I'm taking the sine of. Maybe it doesn't like that.
I think you're already using lowercase a. Maybe that's why.
Oh, it is. It's A. I meant B because that's it. Because it didn't know what to do with it because lowercase a was that crazy curve. I meant B to be my slider this time. Thank you for rescuing me. So the question is, can you see exactly what we saw before, which is as B gets larger and larger and larger, from the air, it seems to be moving along a parabola, but now it's actually just climbing and climbing. You notice it kind of makes a neat sharp turn right there. Can you appreciate the difference in a car between a sharp turn like this? The sharp corner right there, the kind of place you fly off the road, whereas then this is more of a straightaway. Can you appreciate calculus has something to say about that? Like how sharp is that corner? I find that I'm getting lost like looking at this. As soon as I stare at it too long, it starts to look two-dimensional to me. So I'll just move it over a little bit. So can you see it climbing its way up? And notice because it randomly set my limitations for B from -5 to 5, I'm not going to make it to 2 pi because it's going to stop me at 5. But if I did, it would have ended up right over here. So you should find yourself going, yeah, that makes sense. I see that climbing. But what is a vector valued function? It's really looking at that as a vector. In other words, if I say R equals instead of kind of up here, A equals and so forth, it's called vector because we're really seeing this, as I said before. You're really seeing this literally defined as a radius from 0, 0, 0, basically pointing to all the points that create this curve. So you're literally thinking of this as a vector. You see what I'm saying? In other words. In other words, and I'm going to make this change now. It's almost like we're looking at it like this. You see the difference right there? Before it was just an ordered pair, and that created the graph. Excellent. If I put a vector there, now we're actually thinking of it as arrows pointing at it everywhere. Does that make sense? It still produces the same graph. But that's why these are called vector valued functions. And so we're just thinking of it as an arrow pointing to all the points, really. But it's just ordered or pairs, and it's just parametric. There's really nothing different. So, Now let's do something kind of fun. Now, when you were staring at that a minute ago, you probably were very surprised that that was a parabola. Do you agree with that? And not only that, did you notice that where that thing actually lived? I'll go back and share it in just a second, but it kind of didn't go everywhere. Did you notice the parabola stopped? Like it didn't go forever. Aren't you used to seeing parabolas go forever? But it didn't go forever. Like what's going on with that? So, you know, if I let t live between 2 pi and 0, and I certainly would want to include those technically. So that's where this lived. I produced that. And by the way, what happens if I keep going? What if I go on past 2 pi? What's that graph going to do?
Just
Well, T's-
repeat itself.
Yeah, but it's not gonna stay on. It's just gonna keep climbing in the air. Does that make sense? It's gonna get taller and taller and taller. So it's gonna repeat that pattern, but it's gonna not recross its own steps. It's just gonna get taller and taller and taller. We'll look at that in just a second. But I'm imagining you were surprised at the fact that it was a parabola. Parabola? Huh? Why in the world is that a parabola? Like I never would have guessed that. Where's the squared? Do you see what I'm saying? Well, let's actually play with this for a little bit, and I'll actually kind of show you the intuition why. A second ago, I showed you a little of the intuition on how you work your way from a circle, like a traditionally defined circle, and we worked our way to a parametric representation of it. So we went from rectangular to parametric. Well, here we're in parametric. And we got a rectangular parabola. And rectangular, this thing was like a parabola. And so, you know, how do we go that direction? What if I wanted to go the other direction, kind of make sense of this? Well, let's just kind of play with this for a second. You may remember, if you have this handy, what's the cosine of 2x equal to? Like there's an identity for that. What's that equal to? If you don't have it in front of you, don't look it up because I wouldn't think you'd have this memorized. I don't, and I've taught this a lot of times. But if you look it up on your sheet, it's actually 1 minus the sine squared of t. Okay, so that means I could rewrite this equation as 4 times 1 minus the sine squared of t, 2 sine of t.
On my sheet, I have a 1 minus 2 sine squared t.
1 minus 2. Let's fix that. Told you I didn't have it memorized. Yeah, that wouldn't be right. 1 minus sine squared is just cosine, right? So that can't be right. Thank you, Ben. So then there's the equation. Well, now for the first time, you might be seeing a little bit of the fact that there's at least a squared in it now, right? So how are we going to get out of this world? Well, would you agree that you can kind of see it right here? You can see right here that y is 2 sine of t. That's what must be the conversion, right? Isn't that kind of what we did up here? We said, hey, let's let x be the cosine of t, and then we'll see what happens. Well, this is pretty easy to see that y is equal to 2 sine of t. Well, then now that we know that, does it make sense that because I rewrote the x coordinate over there, now I have a shot at writing that, well, in the same way? So let's take a look at what this would say then. If that's true, then this would be x equals 4 times 1 minus 2 times the sine of t squared. Well, what's the sine of t though? Isn't it y over 2? I mean, from this over here, if I resolve that for sine, isn't sine y over 2? Do you agree with that? So I guess we could say, let's see, if I distribute that out, that'd be 4 times 1 is 4. This would be minus 2y squared over 4. So just minus 2y squared, I think. Is that right? Trying to distribute the square of the y over 2 and multiply by 2 and not screw all that up. I think that's right. And so isn't the equation for this, how would I say that? X is well, I guess I could actually just say it like that. In other words, that is my equation. So x equals 4 minus 2y squared. Do you remember what that looks like? Well, notice you see one is squared, one is not. So now it's sort of clear it's a parabola. But notice, what's the difference between the y is not squared and the x is? What do those parabolas look like when you have a y that's not squared but an x that is? What do those look like?
Isn't it open to the left or right? Because it's
Exactly.
negative when it opened to the left.
That's exactly right. This one opens up and down, up if it's positive, down if it's negative. This one opens left and right. And so the y is squared, and because it's negative, this one's going to open to the left. So it's like, oh, I get why that was a parabola now. That's kind of interesting, isn't it? X equals 4 minus 2y squared. That's kind of interesting. So I think we could leave it at that. Yeah, let's leave it at that for a second. So, and again, notice what I did here. I ignored the t. In other words, I ignored this part of it over here because I kind of understand what that's doing. Again, I'm just trying to grow my intuition about what a graph looks like here. I can't really consider all these at the same time. I know that t is just going to take the xy plane graph and just make it climb that and get taller and taller and taller. So I really just looked at the xy answer. And so my intuition, like in a sense, if I'd have put some thought into this, I could have actually maybe figured out, oh, this is going to be a parabola facing sideways. That actually kind of makes sense. I don't have all that in my mind anymore. It wasn't that long ago in this class, we studied that section, parametric equations, and how you can stare at the 4 and the 2 and which one is squared and know exactly what that parabola looked like. But you kind of find yourself needing to look at notes to be able to do that yourself. But remember, you could just find points that work, and that would do it too. Interesting. Let's see. All right, I'm happy with that. Now let's just go play for a second. Let's go graph something. So let's put that back in, and I'll just delete the other stuff since I've given you some intuition about how this works now. By the way, with respect to syntax, remember how I just typed, like, all I did was type this, and then it put all this other stuff in there, and then it even put the word curve in front of it. It's kind of like, oh, you want a curve, and I never said curve. It just kind of did that. But notice the syntax. If you want to just type this from scratch, if you say curve, it's going to ask for X, Y, and Z, and then comma, what's your parameter? Well, in this case, mine was T. I used T, so parameter. And then it says kind of your limitation. In other words, from 0 to 2 pi. So it kind of put that limitation on it. So, I actually have control over all that stuff. So I could come back here in here and say, I don't want that to be 2 times pi. I want it to be 12. And again, is that what you thought you would see? Notice you have to kind of zoom back in order to see it, because right now, notice the Z coordinate is only 7. Does that make sense? So it only shows up to the top of that. But if I back away, allowing Z to get larger, I can see the rest of it. Notice from the air, still just looks like a parabola. I can't really tell that it's back and forth on itself as many times as it is. But that makes sense. It continues to climb. Now, what I want to ask you now is what if I start just playfully, what if I start messing with this number right here? Like for instance, you should be able to tell me this. What if I put a 0.5 in front of that? Instead of just leaving, and I'll take this back to, I'll
It'll
take this
go
back
up
to just 6.
half as slow or half as fast.
Half as fast. Is this what you thought you would see?
Yes.
So yeah, basically the Z values before are now half what they used to be. So it's kind of not climbing as quickly. And again, you can appreciate calculus might allow us to find out, you know, kind of the angle of ascent here, because it looks like it's kind of a consistent angle that it's climbing all the time. So that kind of makes sense. What's going to happen if I do something really weird over here though, and change this from T to something like, I don't know, the cosine of T. Now, I have no idea, because it's kind of, well, I don't know. Let's think about it just a second. If I stick the cosine of T over here, well, think about the values that it will take on. As you work your way from T's of 0 to 2 pi, what values does cosine take on? Let's start from the start. What's the cosine of 0?
It's going to be 1.
It's going to be 1. So that means the first point that you graph is 1 up in the air. You see that, what I'm saying? And then T works its way to pi over 2. What's the cosine of pi over 2?
That's 0.
0. So it's actually going to start at a Z value of 1. It's going to follow the same parabola, but now it's going to work its way down to 0 by the time we get to pi over 2, right? And then it gets to pi. What's the cosine of pi?
That's -1.
That's -1. So it's going to go from 1 to 0 to -1. And then 3 pi over 2, it's back to 0 again. And then at 2 pi, it's back to 1 again. So it's going to go from like 1 to 0 to -1 to 0 to 1. That's kind of weird, right? So I don't know about you, but I'm on the edge of my seat. Bam. And I need to go in here and put 6.28 so that it finishes its path. But notice I didn't change X and Y, so this thing is still a parabola, just like it was before, right? But let's stare at it a little bit. Yeah, there it is at a Z coordinate of 1. And then when I got to pi over 2, which remember was right there, now it has a Z coordinate of 0. And then it worked its way to pi, which was when it was back here, right underneath where it started. But now it has a Z coordinate of -1. And then it had a Z coordinate back to 0 again, because the cosine of 3 pi over 2 is 0. And then it went back to 1 again. So that's kind of cool. This thing's actually, before it was like a path and now it's a loop. That's kind of interesting. But actually, do you see how you can actually think about this a little bit and actually have a sense of what it's going to look like? If you, not if you look at all X, Y, and Z simultaneously, but if you think of the shape as growing off of the X, Y axis. So what's going to happen if I change this 6.28 to go past 2 pi? What's it going to do this time?
Shouldn't it just trace over itself?
Yeah, that's right. And this time, like this time, last time the T got bigger and bigger and bigger. So it was kind of like it climbed and climbed and climbed and sort of went up in the sky forever. But yeah, I think this time it's actually just going to retrace its course, isn't it? So this is kind of a closed shape, if you will. So that's kind of fun. And of course, what's going to happen if I throw like a 2 in front of this right here? What's going to happen if I throw a 2 in front of that cosine?
It's going to move it over 2.
Notice all the Z coordinates just got 2 times bigger. I didn't change X and Y, so it's still kind of that same sideways parabola. But now the Z coordinates just got 2 times larger than they were before. So they went from 1 to -1. Now they go from 2 to -2. Kind of cool. Is that weird? What plane am I looking at here?
Oh, that is weird.
Let's see. Green was Y and
That's the
blue
Y.
was Z. So I'm looking flat at the Z Y axis. And I think I'm seeing a circle. Isn't that trip? Why would that be? Take a look at the equation.
You had a 2 sine and a 2 cosine, so radius of 2.
Yeah, it's like a circle of radius 2, isn't it? So in a sense, of course, it looks like that from that direction. However, don't you find yourself, if you rotate it going, whoa,
Yeah.
I thought that was a circle, isn't that just crazy? I don't know about you, but after I stared at it a while, I thought, oh, it's a circle. But then you move it. Oh man, that's weird. Notice now we're looking at the X and Z plane. Why would that be a parabola? Why would that look like a parabola? It's not as obvious, but that's similar. In other words, from the air, it was a parabola because you had 4 cosine of 2t and 2 sine of t. Well, xz is 4 cosine of 2t and 2 cosine of t. So it's kind of has the same sort of a shape. And so in a sense, that's maybe not super surprising, but again, really powerful. So, ultimately this crazy shape has a circumference in this case, right? Because it's closed. And so, like, what's the arc length of that? What's your slope, at a given point? I mean, that's where calculus is going to come in. So this is really kind of fun. Now let's just kind of play a little bit before we go away from here. I wonder what's going to happen if actually, let's go take this 4 right here and make it like a 7. Wonder what that does. 7 times longer, a little bit skinnier. So that's kind of maybe not super surprising. I wonder what happens if I come in here and change this to a 4. That's pretty fun. Notice from the air, it sort of looks like a 4th degree equation.
Yeah.
Like a 4th degree equation from the air, a W, and yet, isn't that crazy what it actually does in 3 dimensions now? Whoa, it's still a circle. Of course it's still a circle, because did I change Y and Z? Didn't change them, right? So of course it's still a circle, and yet, wow.
I swapped out the Z coordinate for sine of t squared, and it doesn't look like anything. It looks like a combination of a parabola and sine waves.
That's kind of interesting. That's a good choice to, actually I'll do cosine squared since you did sine. Wonder if it lets me do that. You do need to remember you need to zoom out. So that's kind of interesting. You got something similar? This doesn't seem to want to come back on itself.
Yeah, mine looks a little different because I used cosine. Sorry, sine of t squared.
Notice that one all seems to stay in the same plane. That's kind of interesting. It's almost like it's a line from that direction. But again, the big takeaway from this is now you could see a bee outside flying around through the flowers, and you see it kind of flying in some crazy path. And well, this is kind of how you would actually come up with an equation that modeled that path, if you will. And then you could start talking about things like, what path was it on? How long was the path? What speed was the bee flying? Was it going faster when it hit those corners, or was it the same speed? What's the radius of the corner, because it's kind of a sharp corner and so forth. Anyway, interesting Interesting concept. So I would encourage you to continue to play with that a bit. And I did show you that whenever you get sine and cosine involved, because they repeat themselves, in other words, sine works its way from 0 to 1 to 0 to 1 and -1 and so forth. And so that creates really neat looking graphs, I guess that's all I want to say. But you know, you don't have to stick with that. If you stick with tangent, you're going to get something that just explodes off to infinity, and it'll be a little harder for you to kind of get your mind around. But you know, play around with that a little bit. So now I want to show you something extremely cool, and this is pertaining directly to your assignment, but that's also just wonderfully glorious. So let's get after that. So your assignment gives you an equation like this. It says z is equal to x squared. I made up a couple of examples here. Z is equal to x squared plus y squared. So that's a genuinely, well, three-dimensional equation. And I wonder if you could think about what that might look like. We'll get there in just a second. I don't, because I'll graph this in GeoGebra for you. Okay, so there's our equation. So this is like, well, I see the x squared plus y squared, and I think, oh, that's a circle. Except for what you're used to seeing on the other side, of course, is something like this. So if I put a 9 over there, you would say, oh, that's a circle of radius 3. In other words, the z coordinate is 3. Or I guess I could say z is 9 in this case, because I said z is over there, not z squared. But you know, what if there was a 16 over there? You'd say, oh, that's a circle of radius 4. Well, now you're saying no, z is actually 16. Does that make sense? This is z as a function of x and y. In other words, to graph this, you can pick x and y to be anything you want, but whatever you pick, it's going to tell you what answer you get for z. So this time I'm going to do this on my app because I think I might want to be able to. This doesn't work as well, but I think it'll be okay here. So what might this look like? Z equals x squared plus y squared. That's actually an entire surface now. It's not a path. It's a surface. And I say surface because that's not solid. You can't really see this, but it's actually hollow. Now, if you think about it, remember that z was kind of like the radius of the circle, right? So when I put 9 in there for z, that's a circle of radius 3. So it's a circle of radius 3, but since z is 9, then that circle of radius 3 is actually located at a height of 9. Does that make sense? You can kind of see those numbers. So there's 9. Can you visualize a circle that's radius 3 being there at 9? And then if I go to 16, z is 16, then I'm going to have a circle of radius 4. So in some respects, this isn't as surprising as you maybe originally thought. If z was 1, then you'd have a circle of radius 1. And so I zoomed out quite a bit here, but yeah, that's kind of what we would have there. And so actually that's not that surprising, but the key is that it's hollow. It's a surface, not a solid. You understand that? And so that's kind of cool. But now we're going to add something to that. That's not where I wanted to go. We're going to add to it y equals 3x minus 2. So the way this will get worded is, in your assignment, is something like this. Find a vector equation, not a vector valued function, but just a vector equation that means the same thing. for the intersection of these two surfaces. Now, I want you to think about what y equals 3x minus 2 is. What's y equals 3x minus 2 in 3D? Notice there's no z in it. What does that mean? Well, you know what 3x minus 2 looks like. It crosses at -2 and it has a slope of 3. So that's the way you think of that line, right? But what did this say z was? Well, it didn't say at all. So what does that mean z is?
Zero.
Think about this. What if I said graph the equation x equals 3? Notice I didn't say anything about y. Is that the point? Is that it? Is that what the graph of x equals 3 looks like? No y is stated. Therefore, what is y? Y is everything. Y has not been limited. Y is everything. So x is 3, y is 0. That's an answer. So is x is 3, y is 1. So is x is 3, y is 2. So is x is 3, y is -1. So is x is 3, y is -2, and all the decimals in between. And so y is everything in this. It's not 0. So over here, what is z? It's not 0. Does it make sense? The graph you've been doing all your life has a z value of 0. You never thought about it before, but it's like the whole time it was on the XY axis. And so its z value was 0. But what is z here because it's not mentioned? Everything. So what is that going to look like then?
It's gonna be a plane.
Yeah, take a look at this equation a little. This is kind of interesting way to write it. If I rewrite it as 3x and I subtract the y over and I add the 2 over, isn't that what we just studied? Those are planes. 3x, this is a plane. 3x minus 1y plus 0z equals 2. Like, isn't that what planes look like? So it was in disguise, but it's like, that's a plane. We know some things about that now, the perpendicular line and so forth. And so that's actually a plane. So we're talking about the intersection of a plane defined by the line y equals 3x minus 2 and where it hits that kind of that cup. So let's go graph that. I'm thinking that this will graph correctly, but I don't know. Seems like there used to, I was trying to find this the other day, but there's like a setting where you can apparently wasn't it. I don't even know what that did. Doesn't pay to play around too much.
Push the camera button at the bottom right.
The camera. That's taking a picture, I think. It's like taking a snapshot of what I was drawing.
Your camera's on right now, and I think if you were to
It might be the arrow that says like it's in the, or from our screen it'll be in the top left.
Now I've really screwed it up. I don't have anything. This is what old people do when they start pushing everything. You say top left. So that arrow closed it.
Can you press the button that says 3D under the camera icon?
Tried that earlier. Thought I tried that earlier, but apparently I didn't. So there's a way to reset this. You see, I've been messing around with it. Now it's like super tall and it won't let me zoom in on the bottom anymore without it disappearing. And, you know, you kind of spin it all around and it goes crazy. And there's some button it seemed like you could pick. I can't remember what it was. Was it double tap? I don't know. It was like some.
Or are you trying to get the graph to just spin on its own?
No, I'm trying to get it to reset kind of because I've sort of screwed it all up now. It seems like there's a way to reset it. But I just don't
No,
remember
the
what it
normal one,
was.
there's like a home button, but I don't see it here. This is in settings or something.
Yeah, I mean, that's one of the limitations of this app because it could be standard view. There it is. Awesome. How do we get out of that? General. No. Algebra. No. Settings. I don't know. Okay, where were we? So I'm hoping, and I actually don't know the answer to this, I'm hoping it will actually graph the plane when I say y equals 3x minus 2. Oh, good, it did. So that's what it should graph. Does that make sense? Because z has not been spoken for, and so it's everything. And so, again, these are two-dimensional curved surfaces. They're, you know, the cup is hollow. And so can you see how these run into each other? That's what I'd like to find is that, would you agree that where those run into each other is the same path we just described a minute ago? It's like a path in space. And so it kind of looks like a parabola. You agree with that? If I can get that intersection to work, it kind of looks like a parabola. Well, how am I going to do that? So this thing is actually a plane in 3D. Well, we have our description right here. We have everything we need. Notice we have what z is equal to in terms of x and y. And then we have what y is equal to in terms of x. And so in this case, all I need to do is let x be equal to t, because then that would mean y is equal to 3t minus 2. And then I can say z is equal to x squared plus y squared. Do you agree that I now have and it was made of both equations? Do you agree with that? So this business of an intersection, that what I just wrote is an equation in 3 dimensions. And so this is, I'll just leave it written that way, that is our r of t, the same type of equation we were just playing with a minute ago. So I could have made that, right? I could have just said, here's your equation. Now I could clean up that 3t minus 2 squared, but I'm not going to. But let's go graph that. What are you doing? What are you doing? So if I say, I think in parentheses, I can just say x was t. And y was 3t minus 2. It's so much more tedious in this world than it is on your computer where you can type. And then z was x squared, which for us was t squared. And then plus y squared, and y was 3t minus 2. Parentheses, 3 letters, t minus 2, close the parentheses, say squared. Is that okay? It looks like it's okay. Do you see that it's working? So that if I go back and turn the other two off, like, does it make sense? That's, well, notice it looks like a parabola. Notice from the air, it looks like y equals 3x minus 2. Remember x and y? So x and y just looks like 3x minus 2, but notice the z value is very complicated, right? It said square them and add them together. And so although it looks like a line from the air, it's actually a parabola. So it's kind of a parabola that's been, you know, rotated into some weird dimension. So that's kind of cool, actually, that you can kind of find the intersection of a couple of surfaces. That's pretty powerful, I think, don't you? At least it's beautiful. The advantage of being in this world is I can at least throw a picture in here. So let's do that really quick. Let's do one more question like this. And Unfortunately, we'll be out of time. So that graph, I'll add this to the note. That graph is actually kind of our R of t. That's our parametrically defined or vector valued function that is nothing more than just the intersection of these two surfaces that are in 3D. Let's take a look at one more. What if I gave you this? Another example. Intersection of x squared over 16 plus y squared over 9 equals 1. Do you know what that is? You should from this class, although, you know, it's a few days ago. And anybody know what that is? It's got x squareds and y squareds. It's not a parabola. What is it?
The origin's going to be negative 16 and negative 9, or
What do you think of it being as a shape, though?
circle.
It's circle-like.
An ellipse.
But the fact that the 16 and the 9 are there means the radius of the circle isn't uniform all the way around. Yeah, so that's actually an ellipse. So I want to see where that runs into this. Z equals x squared plus y. This is harder than last time. Let's stare back at last time for just a second. The reason last time was not bad is because they kind of were defined in order. In other words, I see that y, it depends on x. So then I can just pick x to be t, and now that takes care of x, x is t. And then y is defined according to x, and so now y has t's, and then z is made of x's and y's, and so you see how it just kind of grew into t. But what am I going to do here? Because notice I don't really have that luxury this time. Like, just like a second ago, I can say, well, z is made of x's and y's, and so if I knew what x and y was, but notice the equation on the other side isn't just a line this time. It's not defined quite so easy. If this squared wasn't here, then that wouldn't be very hard to solve for y. And I probably would let x equal t again, and I would solve for y, and then I would know what y was. Because it is there, it's a little tougher. And because of what I showed you earlier, this is a place where you want to choose a really creative substitution for x and y. Don't just pick t for one of them. When x is squared and y is squared, we can do something better. Now I want you to watch what I pick and see if you can figure out why I did this, because this is not obvious and you have some assignment questions kind of like this. Why would I pick x to be equal to not the cosine of t, but 4 times the cosine of t? What happens to that first expression if you do that?
The 16 will go away.
Yeah, you end up with 16 cosine squared over 16, and the 16s go away. If I then proceed to kind of do the same thing with y, I want you to notice that this is actually a true statement then. Do you see that? It's a very, very surprising choice for x and y here. But notice what they do. I'll write it out. So if I take 4 times cosine t and I square it, and I add that to 3 times the sine of t and I square that, notice you end up with cosine squared t plus sine squared t equals 1. Hey, that's actually true. That's why I chose those. Now, again, is it okay? I'm going to erase this, but is it okay to say, I don't know what to do, I'm just going to let x equal t? Yeah. But if you do that, you'll end up with y equals, you know, the square root of 1 minus x squared, which is now t squared over 9 with a 16 somewhere. Remember the square root only gives you the top half of it and so forth. So this is a very creative and brilliant substitution, as I kind of hinted at the start of this class as well. But now that we have names for X and Y, does it make sense we can proceed over here and come up with a way to say Z? So I can say, okay, well, if that's true, then Z would just be equal to X squared. Well, that's 16 cosine squared T plus Y, which is 3 sine of T. So now I have my vector valued function that is an intersection of those two curves. Again, it's vector valued, or when written like this, because you're basically saying it's all defined by one parameter. As I said before, it's really just a parametric equation. Would you agree that it's very hard to tell what this is going to look like? Well, we did agree, kind of agree, that the XY coordinate is going to create an ellipse, but notice the Z is really complicated this time. Like it's not just T where it gets a little taller and kind of spirals up. Z is super complicated. So I just not really sure what this is going to look like. I really have no idea. So let's go graph all of this. Let's see. I think in the interest of time, I'm gonna do this on my regular screen because I see that we're out of time. So let's go do it over here. So let's graph X squared divided by 16 y squared arrow divided by 9 equals 1, arrow equals 1. Are you surprised by what you see there? You got to go back in your memory to know that's an ellipse. What do you notice about notice you can't even, I have to turn it a little bit for you to even see it, but do you notice that X squared over 16, the radius of the X is 4? That's something you knew a few weeks back. And then the Y squared over 9, the radius of the Y is 3. So it's like a circle that has an X radius of 4 and a Y radius of 3. And yet what is Z? Well, Z is everything. So I get kind of a cylinder instead. So that's true when Z is 1. That's true when Z is 2. That's true when Z is 3. And so I end up with this kind of cylindrical shape. And so we want to know, where does that run into Z equals X squared plus Y? We're not very familiar with that, right? I find myself going, I don't know what that's going to look like. Turn this off. Z equals X. That's a weird looking shape. Notice it's like a parabola, which sort of makes sense, right? Because you had an X squared, and so like there'd be a parabola, but notice it's like a parabola that's been, looks like tilted at a 45-degree angle almost. And so notice Z is changing this time because it depends, like you can pick anything you want for X and for Y, but when you square X and add it to Y, you get some number for Z. I mean, isn't it just cool that it produces that shape? So of course the question is, where do these run into each other? So let's go, seems a little lame that it would just choose them to be exactly the same color. Let's see, I remember I have to kind of zoom. I can't remember how to zoom this. It's like it doesn't want to be. See how my ellipse doesn't want to go tall enough, and yet there was no setting over here to control that. The other day I was kind of playing with this because I'm still just trying to figure this program out. It was like I got it eventually to kind of get taller because I really want this to go up forever, right? And so it's like, why won't you get tall enough to go through that shape? Because this isn't really going to look right unless you can kind of see the whole thing. Let's try home again real quick. I remember I succeeded in getting it to get taller, but I was like, I have no idea what I just did. How did that happen? See if I can control the settings somehow. Is there some way I can say? I want to tell it, I need Y to be Z to be bigger. It's like it won't do it. Well, I guess we'll have to give up for now. Because I want to let you out of here. Well, what was our equation? What was our R of T equation? Again, I'm being lazy and not writing the R of T because I can't. 4 cosine of T was our X, sine of T was our Y, and our Z was more complicated, 16. I think I can get away with this cosine squared. I think I can actually type that. That's one thing about this that I think is intuitive. Like I can sort of type it like we'd like to write it. 3 sine of T.
I think a Y term is 3 sine T. Actually. Is that right?
Yep, 3 sine T. I wrote it wrong in my notes and I was looking at my notes. You're exactly right. 3. And notice that's kind of cool because can you see it didn't work? Like, is that graph, you know, at the intersection of those two? No. So it's like I did something wrong. So 4 cosine of T, sine of T, 3 sine of T. That should be right now. See how it is working now? So the thing I really wanted you to see though, is it actually comes up and turns, it's almost the same graph that we had the other day, but dang it, how do I get that to do that? I'm just gonna play around stupidly again like I did before and see if it'll, seemed like I got in the right position. I just zoomed in such a way that it kind of clicked on it. I don't know, what did I do?
Maybe delete the ellipse and re-add it.
Yeah, mine I was just able to zoom out and I was able to see everything, so I don't know why. Yeah, how that happened.
I mean, when I zoomed out a second ago, you can, like, it's all there now. It's like I have to, I don't know if I have to zoom in a certain way to get it to stay. And you can at least see it right there, even though it's kind of too far away. But oddly, notice that's almost the same shape we had earlier. Remember how that shape was like a parabola from the side? This is not the same parabola. Do you see how it's actually longer on one side than the other? But notice that actually kind of took on a similar shape. That's kind of fun. Guess that's the best I can do right there. So main thing I want you to leave with is just the creativity. Anytime you see sine squared and cosine squared, then choosing something, a substitution to get t involved that is a little more creative. I mean, steal that idea for your assignment. And we'll have a chance to talk about this in class tomorrow too. We're going to go on tomorrow and start looking at calculus. Like, you know, now that we kind of know these shapes exist, what calculus can I do? Throw that 3 in there that Ben pointed out that I left out. What can I say about that arc length and slope and so forth? We're going to start playing with that because now you have a sense of, oh yeah, it is possible to draw a 3D object. But the key is if you don't write it as a parameter like I just did right there with just a t, then you're not going to get a path like a single line through space. You're going to get surfaces, and surfaces would have different questions like what's the surface area of that, you know, cup that we had a second ago, and you know, what's its volume, those kinds of things. It has their own set of calculus questions that actually end up getting addressed in Calc 4. But we're going to look at just the calculus of these vector valued functions right here in preparation for Calc 4. All right.
Thanks, Doug.
Thank you all. Good to hang out with you guys.
All right, thanks.
Is there any difference between arc lengths in this case, or between arc length and perimeter?
No, I just think of perimeter as being a closed shape. So an arc length, like before we had that one that just kept going up and up and up in the air, you'd have to say arc length there because it doesn't stop. But when it came back on itself, then all of a sudden the word perimeter. So no, they're the same exact thing.
Okay. Yeah, because I was looking at the shape and I thought the perimeter made more sense because it was enclosing an area, but the arc length also. Okay. See you tomorrow.
Okay, see you tomorrow.
Oh, actually, I found a fish kind of a graph earlier.
Cool. What
Uh,
a funnish one.
no, it's just shaped like that simple fish that you see on the bumper stickers, the Jesus fish.
Oh, cool. Put it
Yeah.
up. Do you still have it there?
Yeah.
Oh, that's fun.
Yeah, but it looks like this when you go into
Yeah,
3D view.
that's totally cool. Wow, that's interesting. What is that basic shape? Cosine of
It's this one.
t 0.75. That's interesting. That's actually not much of a modification. You changed and
Yeah.
put some.
And then I'm looking for this. This thing looks like a bunch of string, kind of.
Wow.
It's just a massive string down here, and then it unravels.
It finally
that's
lifts
really
off the ground and unravels.
Yeah, it's also really lagging because of how much there is down there.
Mm-hmm. Right, because it sort of circles around really slowly before it starts lifting up in the air. That's really cool.
Yeah. Okay, I'll see you tomorrow.
Good job. All right, see you tomorrow.